little worried about sound. Should be happening. Okay, good. So the topic for this morning is to sort of continue on with MRI. But, you know, I gave you a quick little primer, maybe too quick primer. And for the next hour or so, what I want to do is talk about some topics that are less obvious to people who are doing MRI. There are a lot of new methods out there right now. And many of you probably go to the scanner and you press the start button and you maybe adjust how many images you're going to take and leave it at that, trusting that somebody else has set up the parameters the way you want to. Others of you page through the various options at the scanner console and try to make sense of the many features which are apparently on there. And so one of the things I'd like to do today is help you get familiar with the consequences of these various buttons that are available on the console. I want to first start off talking a little bit about contrast, and this is just a reminder. This is essentially the same as the slide I showed you before, suggesting that a series of 90-degree pulses produced at a rate that is short compared to the T1 relaxation rates of tissue will produce T1 weighted contrast, where signals which have a long T1, like this blue one, regain only part of their signal in the TR period between 90-degree pulses, a consequence of which is when the next 90-degree pulse comes along, that signal that's formed is small, for example, for this blue tissue, whereas for a tissue which regains its signal rapidly, it's relatively large. And then, of course, the signal falls away with T2 contrast. Fortunately, these things are analytic because to a very good approximation, these relaxation rates follow simple mono-exponential time functions. And so if you know the tissue parameters T1 and T2, it's possible to go ahead and directly calculate the signal parameters. From that, you can turn around and say, if I want to maximize the contrast between tissues with, for example, two different T1s, I can go ahead and plug them into this equation, take its first derivative, find when the slope becomes zero. You know that math. And so we have that opportunity. One place in which it's useful is to kind of think about contrast from basic gray-white. And I did show you this slide before without the cool little animation, suggesting that there is some range of TRs where if the TR is very long, you can get most of your contrast by adjusting the TE. So TE is along the right-left axis over here, and your highest contrast comes at long TR and at a particular TE. If, on the other hand, you want to look at T1 contrast, let's see if I can get to a nice position to look at it. TR is along here, and our highest T1 contrast comes at some particular TR. Okay? And you can dial those in. One way in which that might be useful for many of you is thinking about bold contrast, which is the oxygenation level dependent contrast. And as I noted, one of the effects of iron in the blood is to shorten the T2 relaxation rate, in particular the T2 prime relaxation rate, that which is associated with magnetic susceptibility effects. And so you start from a base T2 prime of the brain and shorten it. So when we look at the signal intensity equation relating to T2, you can see that because the relaxation characteristics essentially add as their inverse, that the single T2-like effect, which is shortest, is going to dominate the observed relaxation rate. So when T2 prime is the shortest thing, which it typically is in human scanning, T2 prime dominates the rate. One of the effects of bold is to take the T2 prime and shorten it somewhat. And so if you want to look at the change in signal intensity as a function of T2 prime, you can calculate that according to the equation I showed you before, and this is the plot. And if we, for example, started off with a T2 prime of 45 milliseconds in the brain and bold changed that by a couple of milliseconds to, say, 40 milliseconds, the peak contrast is going to come at a TE of halfway between those two, in this case about 43 milliseconds. So you can go ahead and say, well, what's the best TE to use for my bold scans? And it turns out to be effectively at the T2 prime of the brain. What's the T2 of the brain? Well, you can measure that. And These are measurements made of, this is just a simple multi-slice series where we went ahead and calculated T2 as a function of position. And you can see that in the brain, the longest T2s, even in these, bold type scans, are on the order of hundreds of milliseconds. However, it's widely different in different parts of the brain. For example, in the mesial temporal lobes, the T2s get pretty short on the range of 30 or 40 milliseconds. So your optimal TE turns out to depend on where you are in the brain, which is kind of messy. And so you have to be kind of careful about the consequences of adjusting your TE based on where you're looking in the brain. This is one of these many cases where when you do whole brain imaging, you're trying to ask questions like, where in the brain does X, Y, Z happen? And your MR scans are not uniformly sensitive to different parts of the brain. In fact, what happens is that if you adjusted the TE parameter wrong, you can find that the same amount of activation, like in terms of blood flow changes, is going to have different effects on your statistics based on the variations in T2 that are throughout the brain. So it's a subtle problem. Another sequence which you use routinely, although you may not be aware of it necessarily, is something called inversion recovery. In an inversion recovery sequence, what happens is that before you actually go ahead and make your signal forming pulse, before you apply a 90-degree pulse to the system, you first apply a 180-degree pulse, which takes all of the longitudinal magnetization and flips it over. So remember, the 90-degree pulse took what was effectively stationary magnetization and flipped it into the transverse plane where you had signal formed. A 180-degree pulse flips it all the way down, and you have no signal. Now, why would you do something like that? Well, what happens is that what you do is take the stationary longitudinal magnetization and now flip it all the way to the other side, which means it takes longer to go back to its equilibrium condition. And in fact, what that does is double the contrast range that you have available for T1 weighted effects. So you can kind of see that in this chart. Here now, following the same color conventions I had in the prior slide, the green is something with a short T1, for example, fat. The blue is something with a long T1, for example, water. And the red is something intermediate. And I've chosen a funny time in order to do my signal forming pulse by choosing the time where this red tissue, might have been brain, crosses through zero magnetization at that moment. The 90-degree pulse, therefore, produces no image at all. Whereas from the fat, we get a very powerful image, and from the water, an intermediate image. Now, you could do this, for example, to null out a particular tissue. You wouldn't necessarily do it with brain very often, but you might do it with water. And it's kind of typically done with water, that you can remove the CSF signal from scans. The clinicians do this all the time. For your purposes, what most people end up doing is using a time between the 180 and the 90, which is called the inversion time, or TI, of a couple of hundred milliseconds, say right in here. And there, you have this huge contrast range of T1 effects. And that's the basis of these so-called MP RAGE scans. How many people are doing either MP RAGE or what's it called? SPGR what? SPGR. How many people are doing those? Yeah, good, 100%. So that's the basis on which these things work. And there's a lot of subtlety in setting these up because, in fact, the time it takes to go from your disturbed position after 180-degree pulse back to equilibrium is also made longer by the fact that you're inverting the spins. So the TRs tend to be very long, and you end up with these very complicated trade-offs between the contrast you want to have and the imaging time, which I'm not prepared to, well, I mean, I can talk about it, but I don't have slides on it right now if somebody wants to hear in more detail how that works. Okay. Another topic that appears to the users at the scanner is something called bandwidth. How many people here in this room have noted a bandwidth parameter when they set up a scan? Yeah, about half of them, okay. So it's always available on the console. If you page through the parameter pages on every major manufacturer, you have this thing. And I want to explain what that parameter is because it's actually pretty important. So if you take your image and or your subject, excuse me, and run a gradient left to right, what happens is that now the spins in one side of the magnet, say the right, are processing at a higher rate than the spins at the left hand, right? And so you're separating the spins by frequency. And that's how you make your image. Now, the wider you separate them by frequency, of course, the less energy there is at each frequency. Does that make a certain amount of sense? Right? You're just spreading the signal out. Okay? However, noise in the MR scanner tends to be broadband at all frequencies, essentially equally. So if we imagine this darker blue signal to be this darker blue curve to be the signal in the brain. You can tell this is my brain because that's my big nose over here. So this is my left ear and my right ear. And the signal is highest. It's almost like a shadow now from, I guess in this case, front to back. And the signal being spread out across a wide range of frequencies is relatively smaller compared to the noise. On the other hand, if I concentrate the signal over a narrower band of frequencies, what happens is that the noise is picked up only over that narrower band of frequencies, and therefore I have less noise in the scans and a better signal-noise ratio. Okay? This is actually something that appears in myriad applications. I don't know how many people ever operated recording tape in a studio, but the faster the tape runs, the better your signal-noise ratio for effects that are essentially like this, that you change the bandwidth of these signals. And it's always important in making precision recordings to limit the bandwidth. So in general, the consequence of decreasing the bandwidth is that imaging time is increased. And that has to do with the fact that you're sampling slower to get to lower frequencies, and to take the same number of samples takes a longer time. Okay. This is a very real effect. These are 3 pictures shown with different bandwidths. In this case, the bandwidth refers to the frequency from left to right in the entire image. The low bandwidth scan, which is on the left, you can very, very clearly see details of the thalamus in here, these tiny little real contrast changes. Whereas in the high bandwidth scan, 4 times the bandwidth, it's really too noisy to see that. Does everybody pick that up? Okay, when you look at these pictures, there's something else, however, which is grossly different in these pictures going from left to right. Anybody want to point out the elephant in the room here? Remember those attention experiments where the gorilla walks in while people are playing basketball? It's right here on these pictures. Anybody want to point anything out? I'm sorry? The white strip. That is this white strip? Okay, first of all, what is that white strip? Skin. Skin. So bone produces virtually no signal. Its T2 star is extremely short. Okay, and again, tell me what's different about the white strip. Yeah, so it's on the image on the left, it's moved way over from the brain compared to the image on the right. Okay, and in fact, so look at the distance between the skin and the cortical bone over here on this picture compared to the skin and the cortical bone over here on this picture, which are the same subject at the same location. Right? So that's an artifact. It's an artifact known as the chemical shift artifact. And it refers to the fact that the skin contains a large amount of lipid compared to the brain, which is mostly aqueous. And so here's how that works. Chemistry, right? So this is go back to high school with me for just a slide or two, okay? This molecule here, if I didn't say water on it, I imagine you know that this is water, H2O, okay? This is now fat. Fat is essentially made of long tails of hydrocarbon. So carbon, which has 4 binding sites, you remember, now is attached to, each carbon is attached to, say, 2 carbons and 2 hydrogens. These are covalent bonds. And in a covalent bond, what happens is that the atomic nuclei share the electrons that are around them. And you talk about electronegativity, which is the affinity for an atomic nucleus for electrons. And it turns out that oxygen on its own has a much higher electronegativity than does carbon. The consequence of which is that water forms a bond with hydrogen. It ends up sucking away some of the electrons from the hydrogen. Now, it doesn't really suck them away. They just statistically spend more time around the oxygen atom than they do around the hydrogen atom, okay? Whereas in fat, the electronegativity of carbon and hydrogen are essentially the same, meaning the electrons spend equal time around both. Is that making sense? Okay, now here's this MR thing, which is we talk about nuclear spins as producing most of our MR signal. And in fact, that's basically true. However, the electrons themselves also have a spin resonance associated with them. They also are magnetic because they're moving charges. Okay? And if you imagine you've got a positive charge which is affected by a magnet, then a negative charge, which is also affected by a magnet, is likely to do so in the opposite sense, right? So what happens is that the electrons actually oppose the field that the protons find themselves in, and they reduce the apparent field strength nearby. If you're in a water molecule, what happens is the hydrogens are stripped of their electron cloud, the consequence of which is that they are affected by a larger magnetic field, and they precess at a higher rate. Remember the gyromagnetic ratio and Larmor constant. Okay? So which is the relationship between the magnetic field and the precession rate. So the long story made short is that hydrogens in a water molecule have a higher MR frequency than hydrogens in a carbon molecule. If I go ahead and plot the MR frequencies in, say, a mayonnaise phantom, one of my favorite phantoms. Mayonnaise, as many of you know, is made by basically mixing oil and water, oil and eggs, and in almost equal parts. So what happens over here is that the water, and this is a weird convention having to do with spectroscopy, the water precesses at a different and higher frequency than the lipids do. Okay? We make sense of that? Any question with that? Okay. When you make an image, what you do is separate position by frequency. Therefore, it should not be too very surprising that water and fat that are in the same physical location in the scanner end up showing in different locations on the image because they precess at different frequencies. Okay? And that's the origin of the so-called chemical shift artifact, the thing I showed you with the sideways shifted skin. And it might also follow that the smaller the frequency difference between pixels on the image, the larger the spatial chemical shift artifact. Okay? And you can calculate this very easily. The fat water chemical shift is known to be about 3.5 parts per million. Meaning that if you were at 100 megahertz, that you'd have 3.5 hertz higher, 350 hertz higher spin frequency for water than for fat. And since there's a proportionality between field strength and MR frequency, you can calculate the chemical shift artifact. Now, if you have a fixed bandwidth, so many hertz per pixel, you could therefore calculate the displacement of the fat compared to water. And it goes up with field strength a lot, rapidly, linearly. And so here is now a less magnified view of that brain picture I showed you with the low bandwidth. And it's pretty hard to miss what's happened to the skin. It's in the wrong place. I'll just say parenthetically that all scanners, all commercial scanners now have the frequency axis going from anterior to posterior, not left to right. So the chemical shift artifact is anterior to posterior. Why? You can see the asymmetry of the image, okay? What it actually does is save lives. Because the physicians, when they look at a brain scan, look at symmetry. And they can't help it. We all look at symmetry. And if you have a chemical shift artifact like this, and you're not paying attention, you might turn around and say, there's this ugly looking signal over here on the subject's left, your right, which isn't there on the other side. And the physicians were calling these hematomas, secondary to contusions. People came in with a head injury, they saw what looked like blood to them, and did the obvious thing, which is to break the skull open and try and get it out. Okay? Which is now why we run the frequency encoding the axis the other direction. Now, things magnetize to different degrees, not simply because of their chemical shift, but because different materials magnetize differently. And we have a factor known as magnetic susceptibility, which is the magnetizability, if you will, of a sample. And here's a phantom which has a lot of physical structures in it, the dark area here is basically plastic, the bright area here is basically water, and water and plastic magnetize to a different degree, but the geometry of these things matters a lot for where the magnetic field lines go. So in this particular phantom, when the bandwidth is high, things look round and straight, okay? But when the bandwidth is lowered, that is more frequency difference per pixel, these difference in magnetizability produce clear and egregious shape distortions, okay? That is a huge effect on your particularly echoplanar images. It's the nature of echoplanar scans that their bandwidth along the phase encoding axis is exceedingly low. And therefore, they suffer a great deal of shape distortion. And so the bandwidth, for what it's worth in an echoplanar scan, when you're at the console, is controlled by a different parameter, which is the time between successive lines. And on the Siemens scanner, that's called the echo spacing. And unfortunately, I don't know what it's called on General Electric scanners or other scanners. But the larger the echo spacing, the lower the bandwidth and the higher the distortion. And that's a huge parameter in scans. When I set up functional protocols for here at UCLA, I spend a lot of time trying to optimize the geometry of the scans to minimize this kind of effect. But there are a lot of trade-offs. A lot of engineering goes into the decisions for that. Any questions with that? And does anybody have any observations, seen this kind of stuff before? I'm sure you have. Okay. I want to talk a little bit about scan time. Typically, the amount of time it takes to produce an image is the product of the repetition time times the number of encodings that you do in the scan. In an echoplanar scan, the phase encodes are actually not really part of the imaging time. But in a conventional scan, every single line of the data is separated by a TR. And therefore, the more lines you have in the image, the longer it takes to acquire the image. Some people also do averaging, which improves SNR, equivalent to, if you do 2 averages, it's like doubling the sample size in your population. It just increases the SNR by the square root of the number of averages. People also do 3D encoding. All of you people using SPGR and MP-RAGE are doing 3D scans, which typically have hundreds of lines of data. And on the MP-RAGE scans, typically the TRs are kept to a few tens of milliseconds in order to make the scan times short enough. Actually, there's some other tricks with that. So I showed you this picture relating TR to contrast. Remember, TR increases scan time, and if you'd like the scan time to be shorter, you might want to shorten the TR. The consequence, however, is that it has gross effects on the image contrast, right? You can go from a proton density weighted scan to a T1 weighted scan, which have nearly inverse contrast behavior, and you can reach these horrible points where you have zero contrast in the scans by choosing the wrong combination. So shortening scan time by just adjusting TR is really not a very effective way to fight the battle against scan time, because you're changing contrast in ways that you don't really have direct control of. Now, some years ago, many years ago actually, a gentleman named Erwin Hahn figured out that there is an advantage you can get from not flipping the spins by 90 degrees, but instead by flipping the spins by a smaller amount. And it goes like this. When you flip the spins 90 degrees, you clearly get the maximum signal. You take all the magnetization and make it transverse, okay? If you flip the spins by 30 degrees, that is a third of the way, you get half of the signal, because the sine of that angle, sine of 30, is a half, whereas the sine of 90 is 1, right? So from simple geometry, you can see that a small flip angle produces a disproportionately large signal compared to the amount of rotation the spins have made. Now, why does that matter? Well, because every time you rotate the spins away from their equilibrium condition, the amount of time it takes for this, the amount of magnetization they lose depends on the flip angle. If I produce a 90-degree flip angle, all of the longitudinal magnetization is gone. if I produce a 30-degree flip angle, 1 minus cosine 30 is gone, or something about between 10 and 15%. Not surprisingly, the amount of time it takes to recover your longitudinal magnetization is shorter with a 30-degree flip angle than with a 90-degree flip angle, right? Maybe 90% shorter. Okay? So here's a plot of the relationship between TR and, TR is the ratio of TR to T1, normalized by the T1 of the tissue, and the signal vertically as a function of flip angle. And what you can see is that if your TR is extremely long compared to T1, you get your maximum signal. No surprise with that. On the other hand, if your TR is short compared to T1, what you find is that a smaller flip angle actually gives you larger signal. And so on as you go to shorter and shorter flip angles. And when you start to get to really, really short TRs, tiny fractions of T1, say a tenth of T1, you will have, at 20 degrees, 3 times as much signal as you would have with a 90-degree RF pulse. And when you get even shorter, you might have dozens of times higher signal by choosing a flip angle which is which is smaller than 90. And you can actually calculate the optimal flip angle as a function of TR and T1. And this is the so-called Ernst Angle. If you type Ernst Angle in Google, there'll be 100 little charts and things which you can go ahead and find them. And basically all those charts are the solutions to this trivial equation, which is that the optimal flip angle, which gives you the most signal, is the arc cosine of e to the minus TR over T1. T1 in the human brain at 3 Tesla is about 12 to 1400 milliseconds. And so you're going to adjust the TR, and you can directly calculate these numbers yourself. So everybody good with that? Okay. It's a relatively important effect because in the bold scanning these days, there's a lot of interest in scanning more rapidly. You know, for example, resting state networks, everybody's seen people scanning with 400 and 500 millisecond TRs, which is 1/3 of the T1 of the brain. And therefore, the signal is being punished if you use a 90-degree pulse. And so you really, at TR over T1 of about 1/3, you probably want to be scanning with a flip angle of closer to 60 or 70 degrees in order to get maximum signal, and it's a large effect. Okay. Let me make sure I know where I'm going with these slides. I'm going to skip this one because I've already made the point. Okay, so that's what I wanted to say about contrast this morning. I next want to talk a little bit about multislice excitation. Remember that in order to select a slice of tissue, I transmit an RF pulse at a frequency corresponding to the location in the magnet that I'm trying to image. Okay, and I make the location frequency vary by applying a magnetic field gradient. In this scan, we might have 4 slices, each of which are excited at a different frequency corresponding to different slice locations. Okay, hope that's clear. All right. Now, there are a couple of issues with frequency selective excitation. One is that in order to make a signal of a precisely known range of frequencies, right, you want to go from, say, 100 hertz to 150 hertz and have nothing else. You can do that, but it requires an excitation pulse which lasts for infinite duration, which turns out to be inconvenient. And in fact, the typical approximation to infinity for the time of the RF pulses in a scanner is something like 2.5 milliseconds. So it's pretty far from infinite time. When you truncate these pulses, you make them shorter, you don't really have that precise control of frequency. And what happens is that the slices no longer would have a square profile that is equal energy at all frequency, but they have a profile like this. And so we measure the slice thickness. When you type in 2 millimeters on the scanner, what you're really getting is the full width in frequency at half the maximum. So the full width at half max is what's called the slice thickness. And what this means, of course, is that you have signal coming in from outside of the slice, And you really don't have even signal even from within the slice. Now, that's not so bad except when we start talking about adjacent slices. What happens is that the signal intended for this slice the RF pulse intended for this slice is experienced by the locations to left and right. And if these two overlap in time, what happens is that this crosstalk region experiences a more rapid rate of TR pulses, which means that its signal goes down because of T1 effects. And that crosstalk is problematic. Now, one thing you could do about that is to simply separate the slices. And on the scanner, there's an option to have a slice gap. And what that does is reduce the crosstalk regions. Now, physicians used to freak out about this. In fact, they do still freak out about it. They imagine that in that gap is where the lesion's going to take place, and they're not going to see it. And you know, if you have a 2 millimeter slice and a 25% gap, you've got a 200 or a 500 micron lesion that you're supposed to detect, which is unlikely. But that's the thinking that goes behind this. People do tend to resist the slice gap. Probably most of you resist the slice gap. So in order to mitigate this effect somewhat, people have come up with good strategies for multi-slice MR. So if I am scanning a single slice of tissue at fixed TR, what happens is that I have some time between acquisition of each slice location, during which I'll go ahead and excite other slices. And I showed you that multi-slice thing. And so a typical way you might think about this is I simply acquire the slices in order across the TR sequentially. When you do that, however, the time between excitation of adjacent slices is equal to the TR divided by the number of slices. That makes sense, I assume. Okay? Another thing you might do, however, is instead to acquire the slices in interleaved order. So we acquire first the odd-numbered slices and then the even-numbered slices like this. And what you can see is now that the time between excitations of adjacent slices is maximized, and therefore that minimizes the crosstalk contamination. And this is the so-called interleaved order. Many of you, when you do data processing, see this in your scans, and you might wonder where that's from, and it's in order to address image quality. And the time between slices is instead of, say, if the TR was 1 second and you had 10 slices, you'd have 100 milliseconds between slices in the sequential order. But in the interleaved order, the time between slices is approximately TR over 2, or 500 milliseconds. So it's kind of a big deal, and that's why people do it. Now, when we think about frequency selective excitation, it turns out there's some other tricks that people have come up with recently that are sort of amusing. And hopefully the sound is on for this one. What I want to show you is the acquisition of slices, 4 slices in interleaved order. I didn't mean to do quite that loud, okay? So you get the general idea that different frequencies are exciting different slices, okay? There is now a technique known as simultaneous multi-slice imaging, SMS or multiband sequence. And I want to spend a couple seconds explaining how that works because it will be in all the commercial scanners in the next year, and many of our scanners now. How many people, by the way, are using multiband sequences? Yeah, about a quarter of the people, maybe a little less. You all will be a year from now. And the idea is this, that if I have different frequencies associated with each slice, like this, I could also play them together as a chord. Okay, now what I think you're going to hear is that you can hear all 4 notes in the chord. Okay, and the proton spins experience it exactly the same way. If I send out radio pulses at 4 different frequencies, then 4 different locations in the imager are simultaneously acquired. And you can do some pretty cool tricks with this. So, for example, if you have the multiband factor set to 4, that is 4 slices excited at once, then I cut my imaging time down by a factor of the multiband number. Now, of course, I can also do this interleaving trick and have a gap between the slices equal to their slice width. So here's what that one looks and sounds like. So you see that? that what's happening is in the multiband sequence, we acquire 4 slices at once, and then we interleave in order to get the in-between ones at this sort of optimal rate. And we get these huge speed-ups in the scan. Okay? But there's kind of a problem, which is that all those slices are producing their signal all at once. So since frequency is giving me location within the slice, how can I possibly tell where these signals come from? Multiband sequences take advantage of a very, very clever technique that was originally proposed essentially at the same time by 2 people, Prusman and Sodikson. They did these, however, using slightly different methods, and the Prusman version is a little easier to understand. In what is called sense encoding, what happens is you take advantage of multiple receiver antennas in different parts of the head in order to get positional information. And you do this in a way that disambiguates positional information. And so let me explain it as though we're just talking about a single slice of tissue, not this multiband sequence. We acquire data. I hear my music echoing through somebody's, must be watching real time. So here is an image which requires a lot of lines of data to form. If I acquire only half of those lines, I end up with an ambiguous, oh, you know what, that's my phone is ringing. I end up with an ambiguous image which shows aliasing, fold over of the picture onto itself. Okay? Does that make sense? You acquire it at, well, I didn't really describe aliasing. You acquire a time-varying signal too slowly, and you end up with an ambiguity about the frequency, which in this case looks like this. It's like you flipped the picture around itself. If, on the other hand, you have antennas in different parts of the image, which is different receiver profile, different sensitivity shown here as a function of position, what happens is the same location shows up with a different signal intensity in the 2 coil outputs. And therefore, you have positional information essentially related to the ratio of the signal intensities from the 2 coils. And with that, you can take these aliased images, here from a coil on the front and here from a coil on the back, and disambiguate them and get a full picture. So that's what is known as sense encoding, sometimes called GRAPPA on the Siemens scanner. There's yet some other bunch of terminology in the different commercial products. I'm afraid I'm principally a Siemens user, so I don't really know the acronyms on the other scanners, but people will have seen this. Because this is now a very popular and important technique because it reduces imaging time, smaller number of lines of data. Likewise, you can use this technique in the context of multiband, multi-slice imaging to disambiguate the slice locations because you have different antennas throughout the head. And so here is now receiver profiles from an 8-channel RF coil. In our scanner right now, we have just purchased a 64-channel RF coil, which does further disambiguation and allows us to get even faster imaging times. And these, of course, can all be combined, multiband and multi-slice and GRAPPA and sense encoding, so we get these radical improvements in imaging time. Another way you can address imaging time is by using multi-echo scans. So this is now the raw data space in the MRI, and you'll remember that each line of raw data is collected at a separate TR in conventional encoding, and therefore my scan time is the product of the number of lines times the TR. Okay? However, I showed you a little animation where you can form a spin echo with a 180-degree pulse, and then if you follow that by a second 180-degree pulse, you get another echo. Right? People remember that? So here's the effect of one 180-degree pulse, which forms an echo here. The signal actually reforms in the transverse plane, at which point, and then decays. If I flip that whole system over, the signal reforms again at some later time, a second TE. Now you can carry that to large extremes and have a large number of 180-degree pulses, each of which forms an echo. The magnitude of the echo decreases with T2, but if these things are happening relatively rapidly, that magnitude change is less important. So you can actually populate the raw data space by encoding each of these different echoes differently with the gradients. And so, for example, in a 7 echo series like this, you can get 7 lines of raw data acquired per TR. So now the scan time becomes the TR times the number of lines divided by the number of echoes. So you have 12 echoes, you end up with a 12 times speed improvement in these scans. This is the basis of what's called fast spin echo scanning. It's also used in something called T2 space scanning on these various cameras. It is absolutely part of the standard armamentarium for clinicians using scanners right now. T2 scans, when I started in this business, were taking 30 minutes. These days, with techniques like fast spin echo, they're taking 3 minutes, which is sort of a big deal from the perspective of patients and throughput. Questions there? Good. Moving along. Okay. And of course, you can do this multiple times and get more and more lines of data from this, right? Okay. We recently had our scanner worked on, which gave me the opportunity to collect some nice pictures. And I was thinking about doing a lab tour over for this course, but it turns out to be clumsy with this many people in it. So I thought I'd let you get a look at the inside of an MR scanner and get some idea what's going on. Here the left side cover is removed. Here the right side cover is removed and the patient table is removed. Here we've stripped it down even further. And then if you look inside the modern generation, this week's generation of Siemens scanners, what you'll find inside of it are the features which make your pulse sequence, which is why I'm kind of showing you this. So in fact, these days we have the radio frequency transmitter is actually inside the magnet or inside the magnet covers. And that location is a radical advance because it keeps all of the electronics associated with the scans inside the room, which means there's less leakage of noise through the room through wires that you connect. And so actually, in the current generation of scans, the RF power transmission is over here, and the RF receivers, which pick up our signal, are right over here, and the data are digitized right at the scanner, and then communicated through optical fibers out of the scanner room. So there's no wires penetrating the walls. What that does is massively improve your signal-to-noise ratio on the scans. It's a very, very clever thing. Then start peeling things apart a little further, and you can see now the actual magnetic resonance imaging field gradients, which are these giant coils of wire made to make the field vary with position. And in fact, they're wound concentrically, X on the inside, Y, and then Z on here, and so in layers. And these are the portions of the equipment which play out these sort of features of the pulse sequences. Getting a little further, now we've stripped it down, and you can actually see where the coils are in space over here, but there are some wires coming in here, you probably can't see them very well, which are used to actually make the magnetic field more uniform, right? So-called Shem coil wires. And those have an important effect. Remember I showed you this picture of T2 star in the brain as a function of position. Well, you can actually tune some of that out. That you can make the T2 star more uniform by shimming the magnet. And sometimes you'll see in scans right now patient-specific shimming. Have people seen that? Do people do that? I do that. Everybody in our institution does that. We're on a patient-specific shim. Okay. But you can also produce region-specific shimming. You can go ahead and say, I really only care about the inferior frontal cortex, which, by the way, is a disaster. And you can improve the signal quality at that region by specific shimming. It turns out at the cost of signal quality elsewhere, which is part of the reason people don't do it as much. Is that a question? I'd love it to be. You can measure the field as a function of position. And if people want to talk with me later about how to do that, it's a bunch of cleverness in order to do that. But you can see that the distortion of the field as a function of position is the cause of major signal dropouts in certain parts of the brain. So this kind of region-specific shimming can have a large effect on your ability to do imaging. That is, if there's no signal, it turns out you really can't see functional contrast in that signal. The final couple of slides, I want to talk about some measurement parameters, which you probably should be doing in your own lab. Was that a question? Yeah, grab the mic.
So back to the slide before, we were just saying that with spectroscopy, yes, we do a lot of shimming. But with resting state, is it one possibility? Do people actually shim? I mean, I know you can shim on the whole brain, but is it a smart idea or maybe a wise idea to think about shimming on the regions that we have so much trouble getting in addition to, say, field maps?
So it's a very good question, and it really depends on your sort of thoughtful examination of what the research question is. If you're doing canonical resting state scans, what typically people want to think about is what's happening across the whole brain. And so you don't want to have any particular region go away. And so when you do a whole brain shim on the magnet, that's probably the ideal situation for you. In fact, what the scanner does is a whole head shim, which is maybe not quite as ideal. And you could do a region-specific shim just over the region of the brain, and you can actually ask the scanner these days to shim on a particular volume. On the other hand, if you're interested in the resting state connectivity of the hippocampus to itself, you might be very, very well served by making a region-based shim that just included those regions of the brain. And it would be at significant cost to your ability to see networks throughout the brain. So does that answer your question? Yeah, okay. Good question. Okay, so the bold scans, we typically are looking at tiny signal changes. A couple of tenths of a % in the signal is really not unusual for people to report, although it's probably silly, but people do that. And we look at fluctuations over time. But if the scanner fluctuates in signal over time, it's adding excess noise variance in this, and which makes it harder to detect. Your detection power goes down as your variance goes up. So at our institution, we run a quality assurance protocol essentially every morning, in which we assess the stability of the scanner as a function of time. And these are kind of the raw data plots you might get from that QA protocol. Here is a good day on a good scanner. We can see that now measured as the % signal change per unit time on a phantom now, right, which shouldn't have any. You see fluctuations of a couple of tenths of a %. We typically look at the peak-to-peak variation, and our nominal spec is about 0.2% peak-to-peak is what we'd like to see. Other scanners, this one happens to have been down the street from us, you can see that the peak-to-peak variations are approaching 1.5%. That's a bad day on a bad scanner. Here's a scanner, the red line, that I visited actually in Finland when I was asked to try and help people out with their functional imaging protocols, which were not going so well. And that scanner, we were seeing about an 8% peak-to-peak variation in the signal. Now, if you're trying to measure a tenth of a % on a person when the scanner is bopping up and down by 8%, good luck. Good luck. And for what it's worth, this was a very easy scanner to fix. It turned out that just by looking at the pattern of signal intensity variations, if you knew anything about vacuum tubes, which oddly enough I do, it was possible to immediately figure out that this was a tube, which had to be replaced, and then converted the scanner to this blue line over here. So you know, these things actually can be fixed, which is the reason we do the QA protocol every day. So we look at these things, we have a spec, we report the spec to our service person if it's out of it. Yeah, there's another question back there. Can you get the microphone to this gentleman? Hey, wait for the mic, please.
You said on a good day versus on a bad day?
Yes.
So you mean that it can vary from day to day? And what are the factors that affect the MRI signal?
Yeah, okay, so good question. Yes, it can vary from day to day, not because August 17th is a bad day and August 15th is a good day necessarily, but because the parts on the scanner age. there are things that go on to them, and wires break. Gradient coils in particular have a tendency to fray. Lots of things can affect this. The temperature in the room becomes unstable. The coil connections on the RF system are loose. 100 different things. And the basic QA protocol, which we run, and I'm happy to talk about this with people offside, is an omnibus test for there is something wrong. It's a relatively unspecific test for what is wrong, but essentially those things which would produce damage to our image are what we test for in here. But interpreting the data actually is a relatively subtle art for that. Scanners differ a great deal from site to site. One of the major problems having to do with the quality of the room that the scanners are in. And it's very possible to have radio frequency leakage in the room, which contaminates the scans. And it's extremely easy for an unqualified person to create those leaks. So for example, you plug your computer into something on the outside of the scanner room, okay? And computers, as you know, have things switching in them at millions to billions of times a second in the radio frequency ranges that we scan. Power is drawn by your computer, and the fluctuations in the power that's drawn by your computer appear in the power line for the computer, which can leak their way right through a badly connected audio connector or video connector into the scan room and produce these kinds of troubles. And so the amount of sterility you have to apply in order to get good, clean connections inside and outside of the room is extreme. And we, in my center, we are exceedingly fastidious about this. I'm sort of a tyrant when somebody wants to come in and hook up a new device. Anybody here see me in my tyrant mode with that? Probably. People just turn around and say, I'm just going to plug it in and do something or other. You don't think about these things. So the penetrations inside and outside of the room, these days, our state of the art is everything is done optically. So that we remove any of these kinds of contact problems. We have isolated power strips throughout the scan room so that when people do randomly plug their stuff in, it's unlikely to produce these kinds of ground loops. But the daily QA is one of the best ways that we have of finding that, because you come in and things aren't working right, and you can see those effects. Okay. So the final couple of slides refer to one of the more interesting omnibus tests that's being done now for scanner stability. And this is the so-called Weisskopf Plot, invented by Robert Weisskopf. What you do is basically take a picture of noise, and you take, for example, a few hundred pictures of noise or of a phantom with uniform signal intensity, and you measure the standard deviation within a square region on the scans. Now, assuming that the signal throughout the scan is uniform, what you expect is the standard deviation within that box to go as the area of the box, right? The square root of the number of pixels gives you your best estimate of the mean signal. So if you measure now the box length, just the length of any of its sides, the signal noise ratio should be directly proportional to the side length, right? Because it's proportional to the square of the side length for on the averaging, if that makes sense. I'm sort of confusing the way I'm stating it, but it's a relatively simple concept. So the expected variation should fall as the box becomes larger. Okay, linearly as length becomes larger, the signal variation should fall. However, if you do this as a time series, what happens is you'll see deviations from that effect having to do with fluctuations in the signal. So now, if you plot the theoretically expected change in fluctuation as a function of size against what actually we see in the scanner, is that when the box size becomes large enough that you have an extremely stable estimate of the signal in that box, then the signal intensity variations in time start to take over. And the deviation between these two is what's produced in the Weisskopf plot. And these are Weisskopf plot measurements from 2 different scanners. And these are used as figures of merit when you try to compare scanners, for example, in studies. This is a bad scanner because now with a relatively small region size, ultimately the signal fluctuation is dominated by the scanner fluctuations. Whereas in this scanner, you have a much, much, much larger region size before that takes place. Okay, so that's all I have to say, which leaves me 4 or 5 minutes of questions, if there are any, and thanks. There's a question over here for that mic.
Yeah. Okay, thank you.
Here's a qualified MR physicist, so this was probably not all advanced topics for you, but that's fine.
Yeah, so okay, I have a question. My data has a TR of 2.9 milliseconds, and I've
Milliseconds?
Right? No, seconds. Yeah. Sorry,
Okay.
Seconds.
Right.
Yeah.
Okay. One can do that.
No,
I
no,
just
no,
was
yeah.
trying to be clear.
No, and in articles I see sometimes TR of 1 second.
Yes.
And so I'm wondering, is my data then 3 times worse than data that has 1 second, or is it a square root of 3 times worse? Or I mean, if they use these kinds of partial Fourier and sense, multi-slice, doesn't it have any cost, or is it?
Yeah, okay, so a good question coming from somebody who has the tools and wherewithal to answer these. Virtually all of these effects, the contrast effects, are analytic. So you can go ahead and say, you know, I know the brain's T1, I can figure out what TR is going to be the maximum signal, and if the signal-noise ratio is dominated by a constant noise, then I just maximize the signal. My SNR is highest. At 3 seconds of TR, you're going to have a much higher SNR than somebody else will with a 1 second TR. All other things remaining equal.
Yeah,
Okay.
Yeah.
However, in practice, at high field strengths like 3 Tesla, the signal-noise ratio is really not scanner dominated. It's pretty much dominated by signal fluctuations in the subject. And so what happens is that if you acquire 3 scans that your colleague is doing at a 1 second TR, and the time it took you to acquire 1, what happens is they have the square root of 3 better estimate of the signal at every location in the scan, because those local fluctuations now are averaged out. Okay? Now, that becomes even more subtle when the person in that scanner is doing a task, because now you have other fluctuations which you're actually trying to resolve from this. And there, people push to a TR, which is optimally related to the rate of change of the signal inside the head. And in the bold activation scans, as we talked about on the first 2 days of the course, there is a sort of a natural time course to the signal intensity changes, which people will call the hemodynamic response function. The HRF, from a signal processing point of view, you can consider to be a filter, a frequency filter. And it's a frequency filter that you would calculate by convolving the HRF with the signal time course, or multiplying them in Fourier space. And that convolution will show you what frequencies bleed through once you have the HRF there. Okay? And there's an argument that there's not a lot of point in sampling too much higher than that, because the intrinsic fluctuations of the brain aren't going to be visible when you do this. So it's an exceedingly difficult trade-off. Other parts of this thing are completely non-analytic. When you do the sense encoding, okay, unfortunately, the coils do not ever operate completely independently. They're always coupled to each other by inductive coupling, if nothing else. And that coupling turns out to depend on who's in the coil, because you change the current paths within the coil, and therefore you modify the inductive coupling. And so when you do those sense encoding things, the scanner makes a guess about the sensitivity profile. Usually it's a guess that's based on scanning a phantom, and then it tries to disentangle the data based on those estimates. As you increase the channel count, you end up with a more and more complicated series of overlap, and the efficiency of decoupling does not go up linearly with the number of coils. Okay, so tough, long answer to that question.
So there's a lot of open sharing projects that bring together data from like different scanners. Should we be worried about that? And is there anything we should look for when comparing data from different scanners and different parameters and everything?
Well, you should be worried about it. There are a lot of people who study this. And this particular paper, Friedman and Glover, I think this is the right one, discusses a large number of metrics for comparing across scanners. Gary Glover in particular has put a lot of effort into thinking about how to compare scanners and how to ensure that they're operating the same way, and possibly how to adjust for differences in the scanners. Those effects can be pretty large. So I showed you, for example, these two scanners, they're in a whole different world in terms of the signal quality and detection capability of the scanners. And yes, you should be worried about it. And other things like if you're heterogeneous with field strength, you have both a heterogeneous SNR and heterogeneous relaxation rates. The T1s become increased as you go up in field. So the same TR gives you different contrast. The usable T2s go down as you go up in field, so the same TEs give you different contrast. And then the different vendors. Unfortunately, I mean, they have many reasons for it, but unfortunately for us, their implementation of the pulse sequences are going to differ. So the specific timing of the gradient pulses, although there's this general idea of slice selection, phase encoding, readout encoding, they run the ramp time getting up to the maximum value at different rates. For the diffusion scans, the shapes for the gradients used for the diffusion encoding differ quite a bit across scanners. And these things have significant, although sometimes subtle, effects on the pictures. So it's not easy. It's not easy. In an ideal world, you're scanning all in the same scanner. In a practical multi-site center study world, you should at least try and get people with the same scanner and the same software version. As I showed you those pictures of the scanner taken apart, that was when we had an upgrade to our scanner, and the things like the gradient coil, a minor object, were swapped out, as well as the RF transmitter and all these other things. So you can see these huge differences in how the scanners are implemented at different time points. Practically speaking, most of those effects on our scanner had the effect of improving the SNR, but changing the other contrast behaviors essentially not at all. So your detection sensitivity should be a little better with the new scanner. But as I mentioned when Willem asked, the signal noise ratio is actually dominated by the subject, not by the scanner usually. So we think that pre and post upgrade we're in pretty much the same place in terms of most bold scans. But again, subtle trade-offs. As you make smaller and smaller voxels now, the scanner noise becomes more dominant. And so you see these effects of changes in platform more when you get high resolution scans. Yeah.
So inside our head, is there any places we can roughly use at somewhere basically what you expect, so you can have a comparison between subject taken from different scanners, so have an idea of how different the scanner effects are?
First of all, I'm going out to the world, so I'm not going to talk about different products and what scanners might work better than others. But it's really hard to find rules of thumb for that. It's really hard because it's not ever simply a matter of this scanner is better than that scanner. In terms of like brand X and brand Y are systematically different. It's versions and installations and rooms and other things.
So what I mean is, so, after taking the images from the head, so if we know roughly that a certain part of our head, you expect a very little real signal change. So use that as a common factor between the images taken from different scanners. So have an idea of quality comparison across
Yeah.
completely different images.
So when people do multi-site comparisons, what the physicists always want to do is stick a phantom in, because the phantom's the same. It doesn't fluctuate at all, so don't worry about what part of the phantom you're looking at. When the experimental cognitive scientists, the neuroscientists get involved, they typically want to go ahead and scan the same subject in different scanners. And this is based on the notion that anything that's subject specific as an interaction might be something you can detect. The advantage and disadvantages of both are somewhat complex issue, because me scanned in Tübingen, actually, I'll go a different way. Nico scanned in Tübingen 2 days ago versus Nico scanned in UCLA today on the same equipment, if we could pull that off, are going to be different, because Nikos is a whole lot tireder than he was when he was at home. And the consequences, you do see subject-specific variations, right? I mean, I had coffee at a different time of day, didn't like the person putting him in the scanner, it's cold, it's hot. So those are, it's again, you probably want to look at Glover's work on this, where he really has actually studied this in some detail. That's probably the best point for it. Okay, I see from my happy calendar over here that we are on a break. We have a slightly longer break set up for us right now, both to have questions for here, and also because Dr. Logothetis is going to be addressing us from a different room and location. And so this gives us time to amble over there. Okay, and I want to take a quick look in my own notes and make sure that I know which room we're going to. So give me 1 second. NRB, okay, great. So NRB is the same room that you went to for Dr. Poldrak's talk. It's a roughly 10 to 15 minute walk over there, and I guess that we have therefore a relatively long break. And I'm happy to sort of in an informal way just go ahead and do Q&A on this stuff if people like. So thanks.